Alright, hell yeah. So this is material mechanics, and I wanted to go over beam bending, but we did an introduction to material mechanics. Every time you learn a new concept in material mechanics, I think it's good to go back to the basics. So we went over the basics of material mechanics, kind of from the two fundamental properties that material has strength, and you can measure that strength in pounds, and a material stretches out before it breaks, and so you can also measure that same poundage by a change in length. So hell yeah, intro to material mechanics. So I will just say we need an intro. I think every time someone mentions material mechanics, we have to mention what material mechanics is, because it's this idea that I have. Let's say I have a steel bar, and I want to and it's attached to a ceiling, and I want to hang some load on that. So I always use a 1 inch. This is going to be a 1 inch by 1 inch, so we have an area of 1 inch squared. Now I call this like the strength of steel. Strength of steel, we're going to use sigma, and it's 58,000 pounds per inch squared. So if I have a square inch, I can hang 58,000 pounds. Okay, cool. So that's kind of the first aspect of material mechanics, is like, hey, we got some materials, it's got strength. And it's chemistry, it's atoms. Atoms are held together. There's forces going on, whether it's actual, like if a salt crystal is held together by covalent bonds. Big molecules like metals, they have a lot of electrons in the outer rings. And where I think like iron has, like, don't quote me on this, well, I don't know, it just shares electrons really easily. So it's not like copper, where it's just like wants to like get one, and well, don't quote me on that. I think copper, for electricity purposes, can easily gain and shed an electron, or vice versa, or just shed electrons. But anyway, where steel molecules, there's about 4 electrons that, and damn it, I don't know if it's 4 or 8, but I think you get it. Not really though. But anyway, so steel molecules, they're in a like, all the atoms are in a C together, and then the electrons are kind of moving through them. So the electron connections provide those bonds, and as you pull it, because the electrons are moving in a C, like you can have something, and I would consider it like this. This is a good one to go over. So hey, this is steel. This is a void right there. And then so when we pull on steel, what happens is, like, hey, maybe you get this to happen. I mean, obviously we got more squares, but maybe there you go. So there's 8 squares, and then so when you pull on it, that void goes away. This isn't providing any strength, and then actually when they hook together, the electrons are now mingling, so you can get extra strength. So I guess I wasn't thinking about covering that. That's definitely more advanced. But it is why things, when you do stretch them, they get stronger. And that I will spend just a little 2 seconds on this advanced topic, is because when you put something like a specimen, let's say this 8-inch specimen, and you're pulling on it this way and this way in a machine, it's going to, you can put like that max force, you know what I mean? So like you're going to put a max load over an area, but then as it stretches, it starts to, so like at a critical point, it'll start to stretch, and that's the point where if you let go, like it won't go back to the same shape. Like once you get it like this, it ain't going back to there. All right, hell yeah. And what else? Yes, when you stretch this, like the surface area goes down. So this had a big surface area, and now this surface area is smaller. But we said that this got stronger. So we have to use a way to gauge. If I have a 1-inch bar, I can put 58,000. Let's say that's what I can put. But let's say I have 2 square inches. Well, I can double that. And if I only have half of an inch squared of area, I'd only get half this. Like 20, what's half this? 25. And then plus 4, 29. Yeah, I'd only get 29,000 pounds. Cool. So if you lengthen it, it gets a little bit stronger. But that, you shouldn't be too worried about that. I mean, to make material mechanics as simple as possible is that what happens when you kind of reach this value where it starts to stretch is like, hey, it might fail. Because if I'm hoisting something with a 1-inch steel bar and I accidentally, put too much load, and then this starts moving, like literally the second it starts to move, it can just fail. It kind of just turns into taffy, even though it gets a little bit stronger. But if it don't stop moving, that weight can pull it to failure. Where some designs is like, let's say this is the weight it's attached to, but then there's just like a 1/4 inch gap from the floor, and then so it turns. Let's say it's overweight. It turns. It's going to stretch like taffy, but then this weight just hits the floor after a 1/4 inch. So then this thing, I don't know, is it still taking that load? Well, kind of like a spring. But the only thing that's going to snap it is if it actually lengthens like 30%, 10 to 30%. So that's one of the aspects of material mechanics is like, hey, any chunk of steel, well, 5%, you know what I mean? So if I have a bolt and I'm just, bolts have, bolts with threads, man, they have such inconsistency. But if you have like just kind of a steel bar and you're pulling on it, you should be able to pull 5%, 10% fairly easily. You could be able to lengthen the steel bar 30% before you got 2 pieces of steel bar. So that is, like, steel can get pretty taffy. But hell yeah, there's a lot of components where, just even like a dent in a car. If someone dents your car, well, hey, you got a big old dent, but you don't have a hole through your car, so you can see through the other side. Because when someone starts to like run into your car, they realize that was a bad idea, and then they hopefully have applied the brakes, and then so they're going to apply that dent and then stop. But some critical factors like bridges, you got too many cars on a bridge, too many people on a walking bridge. There's no backup. There's no floor to catch that after this drops a 1/4 of an inch. Okay, hell yeah. So that was pretty broad brush, and that wasn't even the 2 concepts that I wanted to cover. Well, kind of. So yes, steel can get real taffy, 5, 10, 30%. But then what makes material mechanics difficult is you have to work with small numbers. If I had a 1 meter bar, and we'll keep with this 1 square inch. So we have a steel bar, it's going to be 1 meter. This is 1,000 millimeters. This is the elastic property. Every molecule in the universe that's bonded is a linearly elastic, at least for just a little bit. It means that if you apply a little bit of force this way, a little bit of force this way, these distances will 2 atoms together, it's just like putting a force on a spring. Everything is a spring, where if you apply a force to that spring, every spring has a spring constant, and that spring constant says, hey, I'm going to change in length per force that you're putting. So the spring constant K is how much I'm going to change in length, so it might be, some sort of number in meters per force in newtons. So that's kind of the spring constant. And you would have force is equal to the spring constant times that change in distance. And so let's see if that works out. Force would be in, force is the units on this, and we said the units on this is length divided by force. And then the distance is, see, I messed it up. Change in length would be length. So no. spring constant is going to be the number of newtons divided by the length, some sort of length factor. So let's do this again. That was wrong. Always good to use newtons to check stuff like that. So if I have the spring, and I'm sure there's a negative in this. I never like to do it, but for spring is a force equals negative kx. So we have a force here. That's the unit on that. Our unit on distance is going to be a length. And then so how do we, if this is force and this is length, well, we must have to divide by length, cancel that out, and then this must be force. So there you go. Our spring constant is going to be a force divided by a length. I'm sorry about that. Okay, so this is just kind of a property of the universe. All right, new battery. Got it in there. And so, yeah, everything obeys linearly elastic. You know what I mean? You go up to a tank and then push on it. That tank moved. Like molecules in that tank moved. You know what I mean? You can measure the distance that they moved. You know what I mean? All right, cool. So, when it comes to materials, and especially with the ones that we use, wood, steel, even concrete, we keep things in this linear range. Because like this, the second, like I said, you put too much weight in this and it starts to move, like starts to become plastic. We did mention that it gets stronger, so it might stop moving. You know what I mean? You do have that. You have this and this is why you can go inspect bridges and be like, ooh, that looks bent. You know what I mean? Ooh, that looks sagged. That looks permanently sagged because there's no cars on it and it's visibly sagged. Like we built it like this, and then after about 10 years, now it's like this. Is like you can see if something was overloaded. But in some cases, you don't. You design. I mean, if you put too much weight, hey, this is going to break. Okay, so I guess that was a long-winded way to say we don't design things. There's very few things that we design where we want them to fully stretch out or stretch out and then maybe rest on a shelf. This does happen because if you I'm not going to get into that, but it can be very common and safe to have this bar be overloaded because it can stretch 30%. And if you're just going to stretch it, a quarter of an inch, no big deal. Because if this was like a 1 meter bar, like what's 30% of a meter? Well, it's a third of a meter. So you can just kind of visualize that more than 10 inches. You know what I mean? So like you could have a 1 meter steel bar stretch a full inch, like 25 millimeters, and then have it rest on something. It still has very great properties, still super strong. It's just stretched, you know what I mean? And maybe it even got stronger from that perspective. But if you don't have it resting on a shelf and you overweight something, hey, that bar is just going to break because that force is just going to keep pulling it elastically. Cool. And what happens is that you can get up to 58,000 pounds, and then take the weight away, and this 1 meter steel bar will go exactly back to 1 meter. So that's the other property of material mechanics. If things are elastic, you can put a force on them within that elastic range, just like a spring, and then let go of the force. This whole thing goes back to its original dimension. And it's actually remarkable that materials behave that way. You know what I mean? If you were hard pressed, you'd be like, well, no, it seems like any force that I would put on it, it doesn't go back all the way. But in this case, it goes back molecule for molecule. All those molecules are in the same length before stretching as after stretching. You know what I mean? It goes right back to here. And you can put, You know what I mean? It's not even just like, oh, well, if you put 10 pounds on this steel, it's not going to go back to is the application. You can put up to like literally 58,000 pounds on this 1-inch steel bar. And if that's right at that limit, you know what I mean, you take that weight away, this bar goes back to exactly 1 meter. Every molecule is in the same location. And so so that gives us like the high end, because you don't actually get too much more strength. Maybe you can get 68,000 after it stretches and these molecules combine together, and you get, but at that point your area is lower. You know what I mean? So it's bizarre also, because this doesn't come up a lot. It doesn't need to, because you should be working within, you know what I mean, the working parameters of the material. You know what I mean? Hey, let's not put 58,000 pounds at all. Let's have this strength, but let's only put 20,000 pounds for the life of this bar. You know what I mean? Maybe it rusts, and we can still put 20,000 pounds, and we're safe with that. But what happens at this limit of 58,000? Like, hey, as you're pulling 30%, this area is hella reducing. Like we can actually increase the strength on our gauge. Now it takes 68,000 pounds to even keep moving it and keep stretching it. Like the second it starts to stretch, it doesn't require less; it requires more force to stretch that out. Hell yeah, I think this is going to be a video in its own, because yeah, just every time picking up a material mechanics book. And I haven't even gotten to, like, that's where it's like, I might have to end this video just as another introduction to material mechanics. Because it's just the thought process you should be going over every video. And almost all of this, I mean, it is good to know what's happening at a molecular level. The other thing is that at the molecular level, because we are getting this extra strength, and this area is going down, like on our readout, like we just knew that this surface area was 1 square inch. And then on our readout, we're getting 68,000 pounds as our max force. And we're just assuming that that area is 1 square inch. Well, no, this thing necked down hella. You know, the surface area didn't half. But let's say it did. You know what I mean? Because technically it can. This surface area can literally half. And I'm putting now 68,000 pounds over a half of an inch squared. So if I double this number, it's going to be equivalent to 140,000 pounds per inch squared, because I have 68,000 pounds on 1/2 of an inch. Dividing by a half is multiplying by a 2, and we have pounds per square inch of, and this can get up to 120. So, you know what I mean? This is a little bit overshot. The area probably doesn't neck down to a half, but as it's necking down, this area can substantially visually neck down, and you're increasing that strength because that sea of electrons are getting closer together. And then so this brings up the concept of, the only way to talk about the strength of material is in units of like pressure, PSI. This is 58,000 pounds per square inch. It means if I have a surface area of an inch, you know, in this 1-inch square rod, I can pull 58,000 pounds on it. And alright, hell yeah, I know where to go with this. So let's say you have the hydraulic press channel. And so you have your hydraulic press, and then you have just a little 1-inch. So this is that 1-inch square area of steel. But instead of putting 58,000 pounds, you're going to double it. You know what I mean? 2x that 58,000. Over 100,000 pounds. Now, what's going to happen is that this thing is going to squash to a surface area of 2 inches squared. You know what I mean? It's just going to squash out to the side. And if it does, if the metal squashes out to the side, and because because the atoms are just held together by these electrons, you know what I mean, as long as the atoms are close enough together, you know what I mean, especially in the squeezing process. That's why steel you can forge. You know what I mean, as you pound it, you know what I mean, like the molecules aren't like jumping, you know what I mean, as you squish it and pound it and they fly out the side or squish out to the side, they're not like jumping out to the side. They're not exploding out to the side and creating extra voids, you know, as you would get a void here, but then maybe a molecule there and a molecule here. You're not getting that. You're getting a perfect mesh, and so you don't lose those electrical electron connections holding the steel molecules together. So copper's like this, you know what I mean? If you're squashing copper, it's going to squash. You're going to reach you're going to reach that 58,000 pounds. So you still have that. You still have this limit where whether this is a chunk of steel or a chunk of copper, like if it's steel, I can put 58,000 pounds on this little block and then back it off. And guess what? Every molecule in that block is in the same location. And that might be a little high. Like obviously, I mean, it's not like a breaking point. You know what I mean? It might be as low as 35,000 for steel, 4,800, 5,800 might be you know, the point where it becomes plastic as well. But hell yeah, somewhere in that that zone, you might not get plastic. You know, you might reach the boundary of that plasticity, and then and what happens is, like, yeah, I should mention this. So hell yeah, so that void goes away. You turned it plastic. It still has this load on it though. Let's see if it's hanging a weight, and so now this thing, I should exaggerate it and say it. Let's say it looks like this. And then when you back off, so, you know what I mean, we got that void to go away. We put that force on it. It stretched out. We got that increased strength. We talk about that, and that increased strength can be double the PSI, which is pretty bizarre. It might, this actually is tripping me out, because for steel, hell yeah, 50,000. I use 58s, you know what I mean, because it's in books. But 50,000 for steel, it can be as low as 30,000. You know, like just bolts at your hardware store, the low end. Low-end mild steel can be as weak as 30,000, and sometimes you actually use that number in some of the specific problems in the book. Should be 50. You know, when you weld, it's either going to be 60 or 70,000. That's because you have like 60-10, 70-14, whatever. That 7 indicates 70,000. That 6 indicates 60,000. I mean, so even just welding, you know what I mean, you're expecting 60 to 70. So 58's not a bad number to assume. Cool. What was I going? Oh yeah. But with steel, like train parts, like train wheels are, you know, you need a higher PSI, and and then we'll go into that in a second. So you can get steel to have up to 150,000 pounds. So that's going to be your highest rated steel. So just think 3x. So highest rated steel is going to be 3x this 50,000 pounds. Don't remember this is 58 if you don't want to, just 50. 50,000 pounds per square inch is the number that you should just have memorized. And then just these increments that, like, hey, it could be as strong as 3x, and like stainless steel could be 100,000 pounds. You know what I mean? Maybe a little less, but up to 100,000 pounds. And so that's going to be a 2x. So this is your baseline. Stainless steel can be 2x. Grade 8 bolts, 3x. You know what I mean? Even a grade 8 bolt, hell yeah, you get yourself some of that train steel. You know what I mean? You can get yourself some of the best steel in the country going by a grade 8 bolt. So that's your 50, 100, 150, and that's kind of keeps you in that window. All right, hell yeah. Oh yeah. So back to this. So yeah, you get plastic deformation, but even when you let go of this, it goes back just a little bit. You know what I mean? So let's talk about that, because the elastic properties are real stiff. If I have a 1 meter, 100 millimeter long rod of steel, and I put that 58,000, that limit, 58,000 pounds, this rod is going to stretch to 2 millimeters. That's it. It is now going to be 1,002 millimeters. And then I'm going to take that 58,000 pound weight off, and this bar is going to go back to 1 meter, 1,000 millimeters. I can put that load back on, 1,002 millimeters. Take the load away, it goes back to 1,000. Cool. So that's amazing that you can have a full strength. You know, basically that's that yield strength. And when you back it off, it just goes to the same exact shape. So you can put basically the max, and this is very close to the maximum strength of the steel anyway. You know what I mean? If you know, and grade like granted you, what am I trying to say? Yeah, I guess this process is fascinating. I mean, it's just like, well, why don't we make steel out of pulled steel? You know what I mean? If the pressure in this steel can reach now 120,000 after I like reduced its area by half, why not just take two of those bars together and build something out of it? You know what I mean? And so I'm sure in the refining processes to make high quality steel, I mean, sure, there's less voids, you know, better structure, you know, and but essentially you are doing that, like by pulling this and having that steel be stronger per surface area, you have now forged it, but you can't pull it much more. You know what I mean? So if I do take that steel that's all stretched out, that's already 30%, 20% stretched, and then if I start with that, I can't stretch that 20 to 30%. I can stretch that hardly any, maybe hardly less than 1%. So keep that in mind. Okay, but let's go back to this max load or this yield load of 58,000. It'll stretch this 1 meter bar by 2 millimeters, but that's not very much. That's not even, if I stretched it by 1 millimeter, you know what I mean? I have a hard time even doing the percentage. If I stretch this 10 millimeters, that would be 1%. So dealing in percentage is the way to actually start wrapping your mind around these small numbers. So if I stretch this 1 meter steel bar, 1,000 millimeters, by 10 millimeters, you know, I would have 10 divided by 1,000. I would have 1 divided by 100, multiplied by 100%, and then I got 1%. You know what I mean? So that can be easy to see. So what if I stretched it 1 millimeter? You know what I mean? Well, that would be 0.1%. So if I stretch it 2 millimeters, I'm stretching it 0.2%. And hey, that number is not too small. Your brain's not gonna like get fried with 0.2%, even though that's even hard to deal with. And we don't use percentages. It's just a good feel for like how much things are stretching compared to their overall length. What we do use is fraction of the overall length. So if I did stretch it 10 millimeters, the overall length is 1,000. That would be 0.01. And again, this is what we would multiply by 100% to get 1%. Okay, but if I stretched it 1 millimeter for 1,000 millimeters, I would get 0.001. So, you know what I mean? We have to work in a thousandths of, fraction of this whole. This whole length is 1,000. If I stretched it 1 millimeter, 0.001 of that whole length. If I can stretch it 2 millimeters, hell yeah, it's 2 divided by 1,000, and then we get this number that pops up for steel, 002. And that's the elastic limit of steel. If I have a 10 meter long bar, and I'm also pulling on it, hell yeah, I would be able to have 10 times this. So, you know what I mean? 10 meters, I would have 100,000, sorry, 10,000 millimeters, and I could stretch this 20 millimeters. So I could stretch it a little less than an inch, but then when I backed it off, it would go right back to the same shape. Cool. So 0.002, let's multiply that by 100, and we get that 0.2%. Okay, so just compare 0.2% between 5%. Like the fact that steel could stretch visibly, noticeably 5%, still get stronger, have all its same holding capacities, might break. You know, at some point it's just going to break, and, you know, catastrophically. But you have this window of stretch, 5, 10, up to 30% for a perfect specimen. Oh, well, hell yeah, I know how to bring this home now. Okay, so this distance, I'm just making a point that this distance is like super small. So like it's not very much stretch at all. Like it's really even hard, like it's mind-numbing to use these small numbers. The fact that 0.002 is the fraction of, you know, the increase in length. You know, if I have something that's 5 meters, let's say I have a bolt that's 5 inches. And then I start to tighten it, and I can actually, with calipers, I want to do this one. I don't know why I haven't done it, but just take a 5-inch bolt, cheap one, and then start to crank it, you know, and get like a 4-inch chunk of steel, because I think I have that laying around, and then drill a hole through it, and then start lengthening that bolt visibly, and see if I like what would be the length that, to see if my calipers could even measure that. Well, I'd have to take 5 inches and multiply it by 0.002. You know what I mean? I don't even know how to do this. It would be 5 times 2 is 10. But this is going to be, that would be, if this was 10, that would be 10 times 0.001. This is 10 to the negative 3 times 10 to the 1. That's going to be 10 to the negative 2. That's going to be 0.01, 0.01. So 0.01 inches. And I don't know if my calipers, so 0.01 inches. How many millimeters would that be? You multiply by 25, 1 inch is 25.4 millimeters. So 0.01 times 25.4. It would be 0.254 millimeters. So I'm sure my calipers might be able to read that. But a quarter of a millimeter, that's imperceptible, you know, to a human eye. A quarter of a millimeter, it would be very difficult to tell the difference between. But yeah, that's when you've actually overstretched your bolt. That's if you go past with a 5-inch bolt more than a quarter of a millimeter, like it actually permanently stretched. Okay, so I guess we do need to talk about that. Because I can easily, what's the most I can stretch this bolt if I keep within this 5%? So I'm going to go 5, and then what would I do? 5% is, take 5% and divide it by 100. That's going to be 0.05. So take 5 times 0.05, and it looks like I got 25, and then move the decimal, 0.25. So I can move this bolt a quarter inch. So I could stretch this bolt 5 1/4 easily. So that's why I want to do this, because obviously I could read that gauge with my calipers. I could stretch this bolt 5 1/4. And what's going to happen when I stretch it 5 1/4 and then back off the nuts? Is it going to go back to 5 inches? No. Is it going to go back even close to 5 inches? And no. It can only, like all the molecules changed locations, and then you're still applying that, you know, tension. But then when you back off the tension, the molecules just go back to their kind of elastic state. So if you plastically deform it, it's like forging it. You've basically changed it into a new chunk of steel. You've kind of made like a new shape or tool out of your steel, and you're still holding that force. That's why some things, like when you do stretch it, like they run into, like, you know, a ground, and then the force goes away. You know, let's say if it was snow on a roof, it stretched out, but then the snow melted, and then okay, but now you have a deformed roof. And how much did it actually go back? Well, it was as if you forged it that way, and then put it on that roof, and then put that same load on there that kind of caused that. But now because it's all bowed, it can kind of maybe support that or whatever. But then when you back off, the elasticity of the molecules kind of go back to their original shape. But you did forge it into a new shape, so that wasn't very well said. But yes, it doesn't go back very much. It only goes back 0.002. So if I stretch something 5 1/4 inch, it's only, and I said 0.002 of this 5-inch bolt was 1/4 of a millimeter. If I stretch it 5 1/4 inches, it's only going to go back 1/4 of a millimeter when I back off the nuts. So for steel, that's just imperceptible. Like, you really have to be using those graphs to be like, hey, how much does it actually go back? You know what I mean? You follow the plasticity out hella, and then sure, you stretched it out to that point, well, it goes back, down that elasticity curve, which is near vertical anyway. It's not much stretch for things. But then, then the problems in the book, they find ways to like, hey, no, this actually does happen, and you will stretch it, a little bit, and then when it goes back, it'll return to a certain shape, and that is perceptible. Or we do want to know that value. We want to calculate that in. All right, booyah. All right, so now here is the take-home point, and maybe get a card out. Here's going to be the take-home point for material mechanics problems. Is like, you designed something to carry the load. You know what I mean? It can carry this much load, sure. But then maybe it's going to turn into a new shape, right? Forge into a new shape. So we just know that we're going to design it for that, but put this on there. So you're going to be within that elastic range. When you get done with your tool, all the molecules are going to go back to the same shape, and you're just happy. So this, in my mindset, like kind of relearning material mechanics, is like, what's important? Well, I think from a don't get fired and don't kill people, like those are your kind of two goals as an engineer, I would say. Don't get fired, don't kill people. Is that when you design something, you should never have it go into the plastic, It should never go plastic. So, So even like the next time I'm tightening a bolt, that I have it like this. Yeah, this is going to be a great, if I ever come across this. So I got my bolt, and then I have it, nut, and then I got something I'm clamping, big old chunk of steel. And I can probably get calipers. I got 6-inch calipers, so I can caliper this out. And I can read before I tighten the bolt. And let's say it's that 5-inch bolt. And then after I get my reading in millimeters, and then after I tighten it, guess what happens? The bolt lengthened 2 millimeters. Okay, so let's use what we just knew. Like what we're just saying is like, did I over tighten that bolt? Hella. Now it's already permanently plastically stretched. You know what I mean? Now if I back this bolt off, it's going to be 2 millimeters longer, or 1.75 millimeters if you're kind of following, along the, this is its elasticity. You know what I mean? I should only, after I tighten it, I really should just measure 5.2 millimeters. If I did that, that would be a perfect tightening, or 5.3, 5.4. I'm sorry. I chose 5.2 because we said 5.25 millimeters is the elastic limit on that. But there you go. So the next time I tighten a bolt, and I can measure the length before and after. And as this nut is trying to lengthen the bolt, I can measure that. All right, so we started with saying steel had strength, we can put a load on it. And now we're kind of finishing with, like, hey, if I go to tighten this thing and I measure that the bolt changed in length by 0.52, I'm sorry, I'm confused. I'm mixing inches and millimeters, and just because I'm in America and nothing's all in millimeters, we have to use, I would have to call this like a 100 millimeter, basically 125 millimeter bolt. So let's do that. So I have a 125 millimeter bolt because I thoroughly messed that up. I was saying 5 inches plus 0.25 millimeters, which is nonsense. So if this bolt is 125 millimeters, and I go to stretch it, and I measure it at 125.25 millimeters, all right, sweet. I have done a very good job of perfectly tightening it up to its elastic limit. So if I go do this, if I go measure and it's 126 millimeters, I have permanently elastically stretched the bolt, you know what I mean? So let's just call that no bueno. So, you know what I mean? No big deal for this bolt. Like we said, it's the same thing with this. Weight is a 1/4 inch off the ground. Like what? Like and we already know, like, yeah, nothing catastrophic from that. It's so fascinating that even this, you're just like, hey, I have this 1 meter bar, something super heavy, a 1/4 inch off the ground. I can load this up till its breaking point, just on the basis that I know that it can. I know that it can plastically stretch 5, 10, 30%, at least 5%, and so that gap's going to go away. I can put as much load on that as I want to. But some things that don't have anything underneath, well, hell no. This starts to move, plastically deform, this might catastrophically break. So with this bolt, you know what I mean? Like, I don't think anyone's going to bat an eye that we're killing people when we, plastically deform something. But I think it is useful to have that in mind, that it's just like, hey, if something got plastically deformed, like, maybe it could kill someone. You know what I mean? Even if you have a part that you designed that was weak and then, like, bent into something critical and that caused an accident. I mean, I don't know. I don't think it's real easy to get complacent as hell. So you might as well have some little light bulb that goes off to be like, nope. You know what I mean? Or just red flag to be like, well, where's the red flag? Because what happens is you get so involved in too much math, like way too much math, where it's just hard to tell, like you lose your intuition for things. So at least I think that's a good one. It's just like, hey, if you get past this elastic limit, it's like people might die, you might lose your job and stuff. All right, hell yeah. This is really hard for me to bring home, because there's a point where we don't have to measure the weight. Like here I could say, hey, I know this weight's 58,000. But that's why I brought up this one. Because as I'm turning this nut, I'm not measuring the tension. All right, sorry about that. All right, so yeah, when I'm tightening this bolt, I don't have a gauge that measures the tension in this bolt. I don't know how many pounds of force I'm pulling on this bolt. But what I do have is this length. And so that's the fundamental of material mechanics and how the properties of how strong things are. Is that you can either find the force in newtons or pounds, on the amount of material that you're using, whether it's you're pulling this cross-sectional area, and it's the same thing with shearing through a bar. You know what I mean? Maybe just and then a conversion factor of a half. Like, hey, if this is the surface area that I'm shearing through, you know what I mean? Hey, the strength isn't 58,000, it's 58,000 pounds per square inch divided by 2. You know what I mean? So, and then just starts the process of like using theory. And this is an introduction for a topic of beam bending, which actually is like it's pretty cool because it's very perfect. It's very mathematically perfect. It's it's just kind of fascinating. But anyway, so back to this is like, hey, I can measure the force in something, you know what I mean, before I know it's going to break. Or the other aspect of material mechanics is I can measure the change in length in something. If I measure this change in length at 126, well, maybe I went too far. If I measure this change in length of 125.25, and we're saying that's the elastic limit, well, guess what? Guess what the PSI in that in this bolt is? It's 58,000 pounds per inch squared. And so it's good to have in your mind that why I chose a 1-inch steel rod is that I can put 58,000 pounds on it. Well, if I just have a half-inch area, inch squared, I can put 29,000. Quarter-inch, it'd be half of that. You know, it'd be 14,000. Quarter-inch. You know what I mean? And then so forth. So, hell yeah, and that's an easy fractional. You can kind of, a lot of different mathematical ways to just make a simple equation. It's just a linear equation, and it literally starts at 0. You know what I mean? So it's a line that says if you have 0 surface area, you can put 0 force. Hey, you got a tiny, tiny amount of surface area. Well, you can put that much force, and it's a linear line, and that's that steep line, and then you can kind of measure change in length. But we're just kind of measuring the percentage. So anyway, I'm not going to kind of go over that because I think that deserves a whole nother video. But just loosely introducing the idea of PSI. You know what I mean? And knowing that you have this limit 58,000 PSI. What's the surface area? Okay, so that's going to be the tension. This PSI 58,000, and I know it reached 58,000 because I know steel can only lengthen by 0.002 or 0.2%. So those are kind of just kind of the fundamental numbers for steel. The percent that you can lengthen other materials is going to vary, but that's steel is 0.2%. All right, hell yeah. And so I was using this as an introduction for beam bending. And so the take-home point is that you have, this is your length. Let's say it's just 2 steel molecules. I can measure that length. When I pull on it, that length is going to increase just by a little bit. This little change in length, but it's super small. It's 0.002 times the original length. That's that change in length. You know what I mean? And if I get these steel molecules, hey, I can actually move these steel molecules up to 5% the distance between them. I can increase that. I can have an increase change in length of 5% the total length. That's going to be 0.05 times the total length. That's how much I can increase the actual length between 2 molecules. You know what I mean? And we talked about how that is noticeable. 5%. For a max for steel, even might be a min for some specimens might pull 10 to 30% before they do just break. But again, if you're designing anything, you don't want these molecules to get more than 0.2% of their total length away. So and we can measure like a system before and after. And you can even do this. Even with a 5-inch bolt, you should be able to do this visually with calipers. I haven't done it, but I should. Alright, and this is cool because then what happens after this 0.002, if you get these 2 molecules, 0.2% farther away than their original length, well, you get stuff like this to happen. These gaps will close. You get kind of you get a strengthening of the material. You get a reduction of the area, so you're still not able to, you get the strength of, you get extra strength, but your area drops. All right, hell yeah. This is a very good example of 5%. So I'm going to have 20 of these, so bear with me. We got 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. This was worth it because now, and then I just have one other molecule just chilling out. And I shouldn't have put it there. I should have put it somewhere in the middle. It doesn't matter where it is. But when I yank on this thing and get it up to that 58,000 pounds per square inch in whatever surface area this was, guess what's going to happen? No matter where I put this, we can put it right here if you want. This is going to squeeze in the gap. So it's going to occupy that space. And now right there I'm going to have 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. So that's going to be in that space. And that would be a 5%. You know what I mean? That would be an example of a 5% increase in length. And then after that, you know what I mean, it'll probably break. You know what I mean? So that would be an example of like, hey, you got two molecules. They get up to this 0.002 change in length. And you still put that force on them, there is nothing to, as long as you have that kind of max force that caused a 0.002% change in length, there's nothing to buffer that. I mean, you get these farther apart and apply still that same force, these things are going to pull plastically, but it'll probably just snap and break. Where this really shows what happens is like when you do pull it, hey, something else occupies that space, and maybe in that occupation of that, this length increased, and maybe this force slacked out. You know what I mean? This is that's what happens when you you know, if you got a truck, a tree, and you're pulling a stump out, and you give it hell. Throw on the parking brake, maybe do a lateral pull, like a, what do they call that? I don't know, a vector pull? Well, yeah, you do this vector pull, and let's say the car doesn't go anywhere, but all the molecules in the rope kind of maybe stretched out, and then so you get down with the vector pull, and you still have just a little bit of sag now. So that's kind of what's happening in here. Maybe while this molecule went plastic, stretched out, you know what I mean, maybe that change in length reduces the force on the ends and stuff. Alright, hell yeah. So steel is also the same strength and compression, which is bizarre, because copper, actually, if you squash this little chunk of copper, you know, sky's the limit. It'll deform, but man, you can just put an immense amount of load, and you would think that would be the case. If you had two vertical chunks of steel, and then you put them in a vise, it's like, couldn't you just squeeze them for days? Like, wouldn't the elements just flatten out? But this isn't what we see in, and obviously in a structure you have more than just two molecules. But still, even if you had a bunch of molecules, it seems like it would be even more the case that they would just take almost like an extremely high amount of load. But that's not what we see. So this is just on the fly, but let's say we have the same sort of situation where we have this configuration, and then we have two molecules here, and then this configuration. And then so we're going to apply the load and compression. And then maybe here it's just like, ooh, that's kind of obvious. You know what I mean? That's kind of obvious that what's going to happen is that this shape, 1, 2, 3, 4, is going to turn into this. Where those molecules are going to get shoved out, and, you know what I mean? Where, anyway. What's important is to always keep your mind around, like, is this elastic or is that plastic? And this example here, this is plastic. I mean, if a molecule, you know, changes, if we get an increase in length, that's plastic deformation. We got a new shape. And then just keep in mind that elastic deformation is, you know what I mean, these molecules just kind of getting slightly bent out of shape You know what I mean? That reduction in height compared to that reduction might be 0.002. But this is the limit. You go farther than that, for whatever other reason for the molecules in this, is that's going to stay that way. That's going to stay deformed if you get a shape like that. So if you pass this 0.002% change in length compared to this original length, which is 0.002 L naught plus the original length. So this is the change in length plus the original length. This is where you kind of see equations like this, like L naught 1 plus 0.002 or L naught 1.002. But I don't want to get into the math because like I think this gets like even just a simple algebraic concept like that gets hella heady when there's not enough fundamentals understanding of what's going on, and especially when people talk about plasticity, and I talked way too much about plasticity. Even I started this video by showing electrons in a void being, you know what I mean? Like, you don't have to get that specific. As an engineer, you potentially don't have to learn anything about plasticity, and just know that, you know, elastically, you know, within this elastic range is where you should stay to not kill people. And yeah, it's just fascinating. All right, this is where we're going to take it home, because there is some beam, there's some beam problems where, like, man, you can get a deformation of like 2 to 3 inches. 2 to 3 inch, like, just, you know, like this used to be flat, but now there's 2 to 3 inches on this beam. And guess what? It's still within that elastic range. You unload this beam, it's just going to go right back to flat. And so I think that is wild and remarkable when it comes to beams, because axial loaded, we just talked about compressing a little, you know what I mean, something with these. Like, you can't compress it hardly at all. You can't lengthen it hardly at all before you pass that limit of what we're talking about, trying, you know, setting a limit of don't kill people. But when it comes to beams, man, they can deform and then go right back to the shape. So yeah, that's kind of interesting. And the idea with a beam is you have, you know, let's say this is a small little beam. Should have drawn one more. But anyway, what's going to happen is that it can turn into this shape. And so we got 1, 2, 3, those compressed, but then these molecules got farther away. So I can probably draw that better. So we got really compressed molecules, and then these molecules stretched out. So they were all the same size molecules to begin with, but these got farther away or stretched out. And I guess that was almost a bad way to draw it, because if I'm saying the molecules are the same size, we're going to put one there, and one there, and then we got one there, and one there. So these molecules get scrunched together, these molecules get pulled apart, and still the same idea applies. If this was the initial length between the molecules, L naught, if this has a change in length equal to 0.002 times that original length, if the increase in length in this is that much, you know what I mean, hey, that's the limit. All right, hell yeah, and we're almost ready to end this video, but because there's a concept that, like, right in the middle, as long as the beam cross section is the same, right in the middle there will be no change in length, because we had to have squashing of the top, lengthening of the bottom, and the original length was, let's say the length of the beam, we're just going to call it Ly, that's going to be that length, and then so this is Ly minus a change in length, and this is Ly plus a change in length. Sorry to call it Ly, but anyway, so and then this right in the middle is just the original length, and I'm going to make a couple videos because I still doubted that. It's just like, well, like couldn't you have no change in length at the top? And sure, you could make a material that has no change in length at the top and then just really fans out. It would be like Post-it notes. That would be an example. Post-it notes would be able to fan out, but then the original binder of a book or a Post-it note wouldn't change. You know what I mean? If you rubber banded all the pages together, you know what I mean, with a rubber band and glue maybe, and then you opened the spine of a book, that would be no change in length of the spine, but then you would have hella change in length of that part if you considered that a beam, where these are the molecules. But anyway, but yeah, it's fascinating that you can even use geometry to show that, like, maybe we're all good here, because I could have a 1 meter beam. So this is going to be 1,000 millimeters. I could bend it, and weirdly enough, like right down the middle, that length won't change. That'll be still 1,000 millimeters. Because this is like a piece of a pizza. Let's say it's like the crust of a pizza, kind of like a little pie. I mean, here's the radius. Right down the middle is the radius for that middle. And then so the radius on the very edge is just a little bit more. That's going to be half of the height of the beam. And then so this length, this arc length, because it's the circumference of a larger circle. I could take the circumference of a larger circle and say, hey, that's a bigger circumference than this circumference right down the middle. Like, obviously, this circle's larger. And then so I would just measure, I would be able to calculate just using that geometry of like measuring this angle of that arc. And I could see that if I did measure that, and this length was 1,002 millimeters, well, I'm right at that limit, you know what I mean? And if I measure it to be 1,001 millimeter, you know what I mean? Hell yeah, I'm good. And so, and just even that, this is kind of a fascinating problem. I'm not going to do any math on this one, but go do it yourself. You know what I mean? Do a 1 meter, like a 1 meter. I think that'd be pretty good. 1 meter by 25 millimeters. So we got 1,000 millimeters, 25 millimeters. Just know that I could bend it into a smiley face, where the bottom goes to 1,002 millimeters. The top can do equal in compression. The change in length is the same based on those principles that we talked about right here. And the top can get reduced to 90 by 2 millimeters, so it's going to be 998 millimeters. And what we can determine is, what can we determine? Oh yeah, this would be fascinating. What is this height? How much gap is right there? Because I said for beams, it's kind of remarkable. We talked about how this can't stretch hardly at all, 2 millimeters. 2 millimeters is almost imperceptible before you hit kind of that point of no return, plastic or kill people. Where in a beam, you can bend something with obvious deflection, but the molecules aren't getting more than 0.002 of their original molecular, the width between the molecules didn't increase by more than 0.002. So it's just a fascinating thing about this bending process is because the deflections add up, because you had a chunk that was like this, and then now that chunk, each of those chunks is crunched and tightened, and then you're just putting that on repeat. So you have kind of these trapezoidal shapes, and they can just add up hella. And then also shear forces too. I guess we should go over that because shear is a bizarre one. But if we look at, hey, look at these distances. Like these distances between these molecules can't get more than 0.002 times the original width between them. And then so when we shear something, what happens is that this happens. This goes down and this stays put. Now, you can see that the distance between, and even diagonal distances. So like, hey, if that distance is right there and there, this can't increase. And you can just even visibly see this increased. And 0.002, just keep that in your mind that that's really a small change in length. So this is over-exaggerated, and we would have a break right there. Like these two molecules would snap away from each other, and they break at a 45-degree angle. But it's just really fascinating that when I have a line of molecules and I just have a little shear there on those, a little shear there on those, and keep going, because each two sets of molecules can do that. And then if the next set is attached, then it can also drop. And so between the molecules shifting this way, but again, if you're just looking at diagonals, that diagonal distance can't get more than 0.002, but still that adds up. So when you combined like a cantilever, that it can have a hell of a lot of, with a lot of load, it can have shear. The molecules can do that staggered, and then the molecules can also make those little trapezoids. So that is the most fascinating thing about beam bending, of how much bending you can have, but still maintain not killing people, and then within that elastic range that we talked about. So this would be a good math problem to be like 1,000 millimeters. What's the gap that could open up? Maybe I'll do that one in a separate video. But this was pretty good. I think there was moments that were pretty bad, but no, I'm just fascinated. Just all in all, this is, I might make this, I've made this video once before. Like, obviously it gets better every time, especially bringing in more knowledge from the molecular level, the sea of electrons. Sorry, I just looked. I thought there was either 4 or 8, you know what I mean, that get shared. But yeah. And it's the fact that they want 4 and can give, I don't know, yeah, it's just fascinating. I forget how that works out. But it's different than, they're not just needing 1, where copper is really interested in just like kicking off a lone electron. Iron molecules don't just have a lone electron that they're willing to share. I think they each need like a certain amount. And I think that's kind of like, they have 8 electrons in their outer, maybe, and then both are missing 4, but they have 4 in that, so then they share, I think, sorry for just ending on this bad note, but anyway, I need to look that up again. Or not, you know what I mean? Sometimes just having just enough knowledge to be like, yeah, sounds cool, I'm not going to be a chemist, but it is good to know things down at the elemental level. For material mechanics, it gets down to positions, you know what I mean? Again, if these positions get farther than 0.002 change in the original position, that's when you kill people, that's when you lose your job. And that is such a small distance that it can make material mechanics, I don't know, I mean difficult, but then kind of easy. So those are the two aspects of material mechanics. Can you put a gauge and get a force and then measure the surface area of the amount of material, or can you just measure how much the deformation is to determine how much force is on there? And I try to stick with forces as much as possible and try to stay away from the word stress. And in this video, I never mentioned the word strain. All strain is this change in length that we talked about. And so I tried to make it as fundamentally mathematically simple as possible. You know what I mean? And I think that is important because, I don't know, I don't like the word stress or strain. They both sound the same. And, hell yeah. And pressure. Pressure is interesting. So I think we're going to end on that, hopefully in the next 2 minutes. So pressure in your car. You could say, like my van tires are pumped up to 30 psi. So you could say that the strength of the tire itself is 30 psi. What happens is that at, you know what I mean? If I put the weight of the car, like that tire surface is going to flatten into a patch like that. And so same thing with, if I have just a blade of steel that I'm putting in that hydraulic press, and it only has a surface area, let's say 1/10 of an inch, I can only put 5,800 pounds on there. If I do that 5,800 pounds, what's going to happen is bad things, or it's just going to blunten. And if it doubly bluntens, you know what I mean, like gets a contact patch, because let's say I double this, you know what I mean, bad at math, but 10, 16, so I'm putting 1,000, let's just say 12,000 pounds, so let's say I just doubled it, okay? We're going to double it, yet my contact patch just doubled. And so that's what happens with train tires, and that kind of rounds it out, because I talked about train steel being, their strength is 1,500 pounds per square inch, 3 times the conventional 50,000 pounds. And what happens with the train tire is they weigh a lot, and there's enough wheels to do the job, but you still have a contact patch. Contact patch is less than a dime, and a train width is like 2 inches. And so the contact patch is actually the width of like 2 pennies. So the width of 2 pennies for 2 inches. So when you hear the contact patch of a train tire is a dime, it's definitely not in this direction. It's not the width of a dime. It's actually the width of two vertical stacked pennies, and then it's 2 inches in length, and it's probably even less than 2 vertical stacked pennies. But that's the flat spot. So even a steel out of the strongest, it doesn't matter, it could be the strongest thing on the planet, it's still going to flat spot right on that, because its strength, that's the, you know what I mean, the molecules it needs more molecules to support that. So that's kind of a good visual demonstration with your car. Think of your car as the pressure in your tire is the strength of your, quote unquote tire. The pressure in a train tire is pumped up to 150,000 psi. I made a kind of a fun video, a throwback video in the day. I never posted it. It is pretty decent. Maybe I should do that in the next week. Alright, so booyah. So, yeah, you can think of the strength of material as the psi it's pumped up to. And so if you push that against something in a hydraulic press, well, you know what I mean? Well, if it flattens out, hell yeah, you got more surface area, so you can put more load on that surface area. Alright, I think we're going to end it there. Thanks for joining me, and booyah.